So we're going to try to derive the equation of range for a projectile. So the basic premise is you have an object, we're launching off at some initial velocity at some angle, and we're looking for the object to land back at the same height, so basically back on the ground, that is horizontal to the initial launching point. And our goal is to essentially find this distance in the x direction, which is called the range. Right, so it's the displacement in the x direction. So how we approach this problem is there's a key idea, which is you want to find the time vertically for when it lands back on the ground. Use that time over in the x direction, right? Because if you look at the information we have, we can find the initial velocity. So I'm usually going to set up a two-way table with the initial velocity in the x direction and y direction. So that's going to be v initial cosine of theta for the x direction, and then v initial sine of theta for the y direction. The final velocity, we know the x direction, but it's not really useful. The y direction, we don't really know. The displacement, acceleration, and time. Displacement in the y direction is 0. In the x direction is actually what we're interested about. That's the range. The acceleration, 0 in the x direction, negative 9.8 or g. So I'm going to write that as g for the purpose of this in the y direction. And then time is what we're interested in before we find the range. So if you remember two-dimensional problems, usually the connection is the time, right? These two times should be equal, and then using that, we're going to then go and try to find the range. So we're basically going to solve in the y direction first, find time, carry over to the x direction, use that to find range. Now, there's kind of a trick on this problem to simplify the problem down a bit, which is rather than finding the time for when it lands on the ground, we're just going to find the time it takes to reach the top, or the max height point. Because by symmetry, the relationship here, this should be the halfway mark, right? Because it's traveled half the distance to the landing position. So that time is a little bit easier to find. And so that's why we're going to go with that. So T max height is going to be, the main information we know about here is VF in the y direction must be 0 because you're at the top of the projectile motion, right? And then the initial velocity is still the same. The acceleration is equal to G, and the time is what we're searching for, right? So this is a pretty nice setup for this. Now we're going to have unknown v initial sine theta, but that's fine. We're just going to have that answer in terms of those two variables. So the equation here that should be very clear is final velocity is equal to initial velocity plus at. The final velocity is 0. Initial velocity is v0 sine of theta, and then acceleration is gt. Now I should put a minus sign here for the acceleration because it is going downwards, which is the opposite direction as the initial y velocity. So we have that. Right. So solving for this, we end up with, okay, so time must be equal to v initial sine of theta over g. Now remember, this is only the halfway mark. So the actual time we're interested in for this must be double that, which goes to 2v initial sine of theta g. Right? And once again, this is going to be the time that we're going to fix as the landing time, basically the time it takes to reach here, the actual time we're interested in. Now, with that information, if we just set up in the x direction, it's fairly simple because the displacement in the x direction, we're going to use this equation. Displacement is equal to v initial times time plus 1/2 at squared. And this pretty much is the only equation you ever use in the horizontal direction. So if you look at this, the acceleration is going to be 0. So this term just kind of goes away very nicely. And then our goal is to finish setting up for this. So the displacement in the x direction is going to be v initial, which in the x direction is v0 or v0 cosine of theta, times the time, which we just found here. So it's going to be times 2v initial sine of theta over g. So by simplifying this and reducing this down, we should get v initial squared, v initial times v initial, times 2 sine of theta times cosine of theta over g, which if you guys know pre-calc or know your trig formulas, you might recognize that as sine of double angle over g. All right, so this gives us kind of an interesting idea. So with the displacement, or range, we now have a simplified formula that we can now use for whenever we want to find the distance you can travel from a projectile that is launched horizontally or at an angle but lands horizontally at the same level. Right? One interesting feature of this is if I was to ask you what angle would produce, would result in the furthest range, what would that be? So basically, what would allow this to land at the furthest point or the farthest point from the initial launching point? Right? So give you guys some time to think about it. So, assuming you're kicking or throwing the ball or whatever at the fixed velocity, the v initial is fixed. The square is obviously just squaring that. The gravity constant is also fixed. So if you look at this equation, assuming you're kicking as hard as you can or throwing as hard as you can, the only variable that's actually left is just the theta. Right? The 2 is fixed, the sine is fixed. So therefore, the only variable you have any control over is the theta. So then the question you should be asking yourself is, what should I pick theta for to maximize this sine of 2 theta? So sine happens to be maximized at 90. So therefore, what should we pick for theta? Well, it's 2 times theta should give you 90. Therefore, the angle you should pick is 45. So if you launch an object at 45 degrees, it will land at the furthest possible range, assuming that you're landing once again horizontally on a flat surface. If you're launching into like a cliff or you're shooting upwards, right, hitting a taller building, or you're launching from a cliff and it's landing at a lower point, then obviously all of this goes out the window. But assuming it's a horizontal projectile, this is one of the key ideas you can use to solve for the range. Right? Hope that helps.